Hello viewers, in today's class we are going to discuss yet another important problem from definite integrals, right? So in this lecture we'll learn how to find the values of this type of definite integral using the concept of Laplace transform, right? So in this lecture we'll see how easily we can solve these type of integrals by using one important property of Laplace transform, right? So let us start. So before proceeding further, let us quickly see the definition of Laplace transform of a function, right? Now see, suppose we have a function, say f of t, right? And if we want to write the Laplace transform of this function f of t, then the Laplace transform of f of t is given by this integral, that is 0 to infinity, and we have e raised to minus st, and here we have f of t dt, right? So this is the definition of Laplace transform of a function f of t, right? So here to evaluate this integral we are going to use straight away this definition, right? So now let us first call this integral as I, right? Okay. Now see, let us see this structure of this integral, right? Now see, if we write this integral as I is equal to 0 to infinity, and if we write it like this, that is e raised to minus st and t sine t dt for s is equal to 3, right? So if we consider this integral, right, so here we can differentiate these two integrals by writing this integral as I1, right? So if we suppose, or if we let this integral I1 as 0 to infinity e raised to minus st t sine t dt, and for s is equal to 3, this integral I1 reduces to our original integral I, right? So what we have done here, if we wish to solve these type of integrals, then what we usually do, see here we have a term e raised to minus 3t, right? And apart from this term e raised to minus 3t, we have t times sine t, right? So if we take t sine t separately here, and e raised to minus 3t can be written in general as e raised to minus st, right? And if we take the particular value of s as 3, then I1 reduces to our original integral I, right? So whenever we solve these type of integrals, we always write the integral in this form, right? So we introduce a parameter s in the integral, in the given integral I, right? So why we have introduced this parameter s? Because see, the definition of Laplace transform of f of t goes like this: 0 to infinity e raised to minus st f of t dt, right? So now if we compare this integral with this one, then see here we have e raised to minus st, right? And for f of t we can write this function, right? So here we have f of t as t sine t, right? So now if we compare this integral with this one, then we can readily see that I1 is nothing but the Laplace transform of this function f of t, right? And we can now write this as Laplace transform of t sine t, right? So here the basic concept is to convert the given integral in terms of Laplace transform of some function, right? So here we have e raised to minus 3t and t sine t, right? So we'll write this integral as the Laplace transform of t sine t, right? Okay, so now to find out the value of this integral I1, we have to find the Laplace transform of t sine t, right? And in order to find out the Laplace transform of t sine t, we'll use one very important property of a Laplace transform, right? So let us first quickly write that property, and then we can readily apply that property to get the value of I1. So now see, we have an important property of Laplace transform, that is, if we have a function say t raised to n f of t, then the Laplace transform of this function t raised to n f of t is given by a minus 1 raised to n, and the nth derivative of the Laplace transform of f of t, right? And if we write the Laplace transform of f of t as capital F of s, then here we can write capital F of s, right? So the Laplace transform of t raised to n f of t is given by minus 1 raised to n, and the nth derivative of the Laplace transform of this function f of t, right? And now see, here we have to find the Laplace transform of t sine t, right? So if we compare t sine t with this one, then we can see that the value of n is equal to 1, right? Because here we have t sine t, right? And the value of n is equal to 1, right? So if we apply this property to this function t raised to 1 sine of t, then we can write minus 1 raised to 1. Here we have n equal to 1, and f of t is equal to sine of t, right? So we have minus 1 raised to n, and the first derivative, because n is 1, so we have the first derivative of the Laplace transform of this function f of t, right? So we have f of s, so minus 1 raised to 1 is minus 1, so we have d by ds of f of s, and f of s is the Laplace transform of f of t, right? So here we have Laplace transform of f of t. It implies that we have to find the Laplace transform of sine of t, right? And now we know an important result, that is the Laplace transform of sine of at is given by a divided by s square plus a square, right? And see, here we have to find the Laplace transform of sine of t, right? So if we take a is equal to 1, then the Laplace transform of sine t is given by 1, taking a is equal to 1, so we have 1 over s square plus 1 square, that is equal to 1 over s square plus 1, right? So now we can write minus d by ds of the Laplace transform of sine t, which is 1 over s square plus 1, right? So now we have to find the derivative of this function 1 over s square plus 1 with respect to s. So now let us find out the derivative of 1 over s square plus 1 with respect to s, right? So we can now write it like this: d by ds of s square plus 1 raised to minus 1, right? Okay, so now here we can easily find out the derivative of s square plus 1 raised to minus 1 with respect to s. So we have minus 1, then we have s square plus 1 raised to minus 1, and then by chain rule the derivative of s square plus 1 is equal to 2s, right? So now see, minus and minus becomes plus, and here we have s square plus 1 raised to minus 2 times 2s, so that is equal to 2s over s square plus 1 raised to uh, power 2, right? So the value of this integral I1, which is equal to 0 to infinity e raised to minus st t sine t and dt, is equal to 2s over s square plus 1 raised to power 2, and we can see that I1 is a function of s, right? Okay, so now see, with the help of this result we can easily find out the value of our original integral by taking s is equal to 3, right? So if we take s is equal to 3 in this integral, then I1 becomes equal to I, right? So the value of I can be obtained by taking s is equal to 3 in this expression, right? So we have 2 times 3, then we have 3 square plus 1 whole square, so this is 6 divided by 9 plus 1 square, that is equal to 6 over 10 square, and that is equal to 6 over 100. And if we simplify it, so we have 3 over 50, right? So viewers, the value of this integral I is equal to 3 over 50, right? So in this way we have seen that by making use of the concept of Laplace transform and this property of Laplace transform, we can easily solve these kind of integrals, right? So using this result, we can find out the values of these kind of integrals, right? So for instance, let us take this example. Suppose we have to find the value of this integral 0 to infinity t times e raised to minus 4t sine t dt, right? So now if we compare this integral with this one, then we can easily see that we have t sine t and e raised to minus 4t. So the value of s is equal to 4, right? So the value of this integral can be calculated directly by putting s is equal to 4 in this result. So we have 2 times 4, then we have 4 square plus 1 whole square, so this is 2 4s are 8, and this is 16 plus 1 17 square, that is 8 over 289. The square of 17 is 289, right? So the value of this integral is 8 divided by 289. Now let us take one more example. Suppose we have to find the value of this integral, right? So if we compare this integral with this one, then we have t sine t, e raised to minus t, right? So the value of s is equal to 1, right? So taking this value in this expression, the value of this integral is equal to 2 times 1, taking s is equal to 1 in this result. So we have 1 square plus 1 whole square. So this is 2 divided by 1 square is 1, 1 plus 1 2. So we have 2 square, so this is 2 over 4, that is equal to half. So the value of this integral is half. Viewers, in today's class, we are going to discuss one important and conceptual integral, right? So here we have to find the value of this integral, that is 0 to infinity e raised to minus 2t sine t divided by t, right? So viewers, in our earlier video, we have seen one integral which was similar to this integral, except that in that case we have this t in the numerator, right? So in this lecture we'll see this integral in which this t is in the denominator of sine of t, right? So let us start. So now to evaluate this integral, we'll make use of the concept of Laplace transform, right? So we'll see how easily we can solve these kind of integrals using the properties and definition of Laplace transform, right? So now to apply the concept of Laplace transform, let us consider the integral I, that is 0 to infinity e raised to minus st and sine of t divided by t, right? So here if we take s is equal to 2, then this integral reduces to this one, right? So here our aim is to find the value of this integral in terms of s, right? And once we obtain the value of this integral I in terms of s, then we can easily find out the value of this integral by taking the value of s as 2, right? So our aim is to find a more general integral and then to obtain the value of this particular integral by taking s is equal to 2, right? So we have considered this integral I as 0 to infinity e raised to minus st and sine t over t, right? Okay, now let us consider this function as f of t, right? So if we take f of t as sine t divided by t, then we can see that this integral I, it becomes 0 to infinity, and we have e raised to minus st f of t dt, right? So now we have obtained this integral, and we can easily see that this integral is nothing but the Laplace transform of this function f of t, right? Because we know that the Laplace transform of some function, say f of t, is given by this integral, that is 0 to infinity e raised to minus st f of t dt, right? So this integral I is now reduced to the Laplace transform of this function f of t, which is sine t over t, right? So now here we'll write sine of t over t, right? So once we find the Laplace transform of sine t over t, we'll get the value of this integral I, right? So here now we'll use an important property of Laplace transform. Now see, we know that the Laplace transform of g of t divided by t is given by this integral, that is s to infinity, and the Laplace transform of this function g of t, right? Where g of s is the Laplace transform of g of t, right? So here to get the value of this expression, that is Laplace transform of sine t over t, we'll use this result, right? So we can now have I is equal to Laplace transform of sine t over t. So if we compare this expression sine t over t with this one, then we can see that here we have in the denominator t. Here also we have the denominator t, and g of t is sine t, right? So g of t is equal to sine of t. So Laplace transform of sine t over t can be written as this integral, so s to infinity and g of s. Now g of s is the Laplace transform of g of t, and g of t is sine t. So we have the Laplace transform of sine t, right? And we know that the Laplace transform of sine t is 1 over s square plus 1, right? We know that the Laplace transform of sine at is equal to a divided by s square plus a square, right? So if we take a is equal to 1, then the Laplace transform of sine t is 1 over, because a is 1, so we have 1 over s square plus 1 square, that is 1. So here is the result. So the Laplace transform of sine t is 1 over s square plus 1. So now we can take the value of g of s as 1 over s square plus 1, right? Okay, so now what we will do here we have g of s and ds also, right? So now we have a simple integral here, because we know that integral dx over x square plus 1 is equal to tan inverse of x, right? And here we have the integral in terms of s, and we have 1 over s square plus 1. So the integral is tan inverse of s, and the limits of integration are from s to infinity, right? So now we can substitute the limits and we'll take the difference. So we have tan inverse infinity minus tan inverse of s, and tan inverse infinity is pi by 2, and this is simply tan inverse of s, right? So now we have this expression, right? So tan inverse infinity is pi by 2, because tan of pi by 2 is equal to infinity, which is not defined, right? So viewers, the value of this integral in terms of s is given by pi by 2 minus tan inverse s, right? And we can see that this value is a function of s, right? So the value of this integral depends on the value of s. So now if we take different values of s, or the permissible values of s, then we can evaluate different integrals, right? So here if we take s is equal to 2, right? In this integral, if we take s is equal to 2, then we get this integral, because here we have e raised to minus 2t, and here we have e raised to minus s of t, right? So taking s is equal to 2, the value of this integral I is pi by 2 minus tan inverse of 2, right? So the value of this integral is equal to pi by 2 minus tan inverse of 2, right? So viewers, this is how, by making use of the concept of Laplace transform, we can easily find out the values of these type of integrals. Now suppose we have to find the value of this integral, right? Now see, if we compare this integral with this one, then see, here we have sine t over t, here also we have sine t over t, and here we have e raised to minus t, and here we have e raised to minus st. So the value of s is equal to 1, right? And if we take this value of s is equal to 1 in this result, then the value of this integral is pi by 2 minus tan inverse of 1, because s is 1, so this is pi by 2, tan inverse 1 is pi by 4, and this is 4, then this is 2 pi minus pi, that is pi by 4, right? So the value of this integral is pi by 4. Hello viewers, in today's class we are going to discuss yet another important and very conceptual problem from definite integrals under the topic differentiation under the integral sign, right? So here we'll solve this integral which is from 0 to infinity and 1 minus e raised to minus 2x divided by x times e raised to x, right? So in this lecture, we'll learn how to find the value of this integral using the concept of differentiation under the integral sign, which is also known as the Leibniz Integral Rule, right? So let us start. So now see, here we have to find the value of this integral, right? So what we do when we apply the concept of differentiation under the integral sign, we introduce a parameter in the given integral, right? So here what we will do, we'll take an integral which is a function of some parameter a, and we can write I of a as 0 to infinity 1 minus e raised to minus ax divided by x times e raised to x dx, right? So what we have done here, we have introduced a new parameter or variable a, and we have written this integral as a function of a, right? So we'll try to evaluate this integral, and when we come to the final step, we take the value of a as 2 to get the value of this given integral, right? So here we have introduced this parameter a, and we have made this integral as a function of this parameter a, right? And we'll differentiate this integral with respect to a, keeping the variable x as constant, right? So we'll partially differentiate this integral with respect to a. So let us differentiate I with respect to a. So we have del a of I of a, and here we write del of del a, and the integral is 0 to infinity 1 minus e raised to minus ax divided by x times e raised to x dx, right? Now see, we can take this operator, that is del by del a, inside the integral sign, right? So we can now write 0 to infinity, and we can take this operator del by del a inside the integral sign. So we have 1 minus e raised to minus ax, and here we have dx divided by x e raised to x, right? So when we differentiate this integrand, then we differentiate it with respect to a partially, keeping x as constant, right? So now we have 0 to infinity, the derivative of a is 0 being a constant, and here we have the derivative of e raised to minus ax as e raised to minus ax, and here when we apply the chain rule, then here we have simply minus x, right? Because the derivative of minus ax with respect to a is minus x, and here we have dx, and this is x e raised to x, right? Now see, this x and this x get cancelled, so we have now minus minus becomes plus, so we have 0 to infinity, and here we have e raised to ax divided by e raised to x dx, which is 0 to infinity e raised to ax minus x dx, right? So we can now write it as 0 to infinity. Then here we have minus sign, and here also we have minus sign, right? So we have e raised to minus x, and we can take minus x common, so here we have a plus 1, right? So now we have this integral to evaluate. So now we have del by del a of I of a as this integral, right? That is 0 to infinity, and here we have e raised to minus x and 1 plus a, right? Okay, so now see, we know that the integral of e raised to mx dx is equal to 1 over m e raised to mx, right? So here m is minus 1 plus a, so we have the integral as minus 1 over 1 plus a, and we have e raised to minus x 1 plus a, and the limits of integration are from 0 to infinity, right? So now we have minus 1 over 1 plus a, and substituting the limits here, we have e raised to minus infinity, because we'll take x is equal to infinity over here, so we have minus e raised to minus infinity, then we have e raised to minus 0, right? And we know that e raised to minus infinity is 1 over e raised to infinity, and this is a very large number, so the value is 0, right? Because e raised to infinity is infinity, so 1 over infinity is 0, right? Okay, and e raised to 0 is 1, right? So now we can write this expression, that is del of del a of ia is equal to minus 1 over 1 plus a, and here we have 0 and here we have 1, right? So this is minus minus plus, so we have 1 over 1 plus a, right? So now viewers, here we see that we have a differential equation, right? So we have this differential equation. So integrating both sides, we can write it as del of IA is equal to del A over 1 plus A, and now integrating both sides, right? So this is a differential equation, because whenever we apply the concept of differentiation under the integral sign, we introduce a parameter and then we differentiate the integral with respect to that parameter, and then finally we get a differential equation as we have obtained here, right? So now we can integrate both sides with respect to a. So here we have simply I of a, and here the integral of dx over 1 plus x is a log of 1 plus x, right? So here we have log of 1 plus a, and c is the constant of integration, right? So now our aim is to find the value of a, right? So for this, what we do, we use the initial value conditions, right? So what we will do, let us take a is equal to 0 in this integral, right? So when we take a is equal to 0, then I of 0 is equal to 0 to infinity 1 minus e raised to 0 x e raised to x dx, because when a is 0, then we get e raised to 0, and e raised to 0 is 1, so we have 1 minus 1 x e raised to x dx, so this integral is 0 because 1 minus 1 is 0, right? So we get the condition that when a is 0, then I of 0 is 0, right? So applying this condition to this equation, we have I of 0 log of 1 plus 0 plus c. So I of 0 is 0 and the log of 1 is 0, because the log of 1 is equal to 0, and here we have c. So this implies that c is equal to 0, right? So now we have obtained c is equal to 0, right? So taking c is equal to 0 in this equation, we obtain I of a is equal to log of 1 plus a, right? And always remember that this 1 plus a should be greater than 0, right? So a should be greater than minus 1, right? So here when we have assumed this parameter in this integral, then the condition which is to be imposed on a should be a greater than minus 1, right? So viewers, the value of this integral, because I of a is equal to this integral, so we have 0 to infinity 1 minus e raised to minus ax, x e raised to x dx is equal to the natural log of 1 plus a, where the condition is a is greater than minus 1, right? So now we have to find the value of this integral, right? And we see that here we have e raised to minus 2x. So if we take a is equal to 2 and in this integral, then we get this one, right? So we have 0 to infinity 1 minus e raised to minus 2x, x e raised to x dx, that is equal to log of 1 plus 2, that is log of 3, right? So the value of this integral is equal to the natural log of 3, right? Now suppose we have to find the value of this integral, right? So what we will do, we'll compare this integral with this one, right? So the value of a is equal to 1 over 2, right? Because this is e raised to minus x over 2, this is e raised to minus x. So if we compare this term with this one, then a is 1 over 2, right? So the value of this integral can be calculated directly with the help of this result. So a is half. So the value of this integral is 1 plus half. That is the log of 3 over 2, right? Now, similarly, if we wish to find out the value of this integral, then we can compare this integral with this one. And if we see, here we have e raised to minus x, and here we have e raised to minus ax. So if we compare this term with this one, then the value of a is equal to 1, right? So the direct value of this integral is log of 1 plus 1, and that is equal to log of 2, right? So viewers, this is how by making use of the concept of differentiation under the integral sign, we can evaluate these kind of integrals. Hello viewers, in today's class we are going to discuss yet another important and very interesting definite integral, right? And in this class we are going to discuss this important integral which is 0 to 1, and the integrand is x cube divided by square root of negative of log of x, right? And here log of x is the natural log of x, right? So here the base is e, right? So what we will do here, we'll make use of the method of substitution, right? And then we'll apply some important results from gamma function, right? So let us start. So let us take this integral as I, right? So here, first of all, what we will do, we'll take u is equal to log of x, right? So negative of log x. So here I will assume a new variable as u, and u is equal to negative of log of x. Now let us differentiate this expression with respect to x. So du over dx is equal to negative of 1 over x, right? Okay, now see, we have u is equal to negative of log x. So from here we can write log of x is equal to minus u, and from the definition of logarithms, so we can write x is equal to e raised to minus u, right? Because here the base is e. So we have this expression which connects x and u. So x is equal to e raised to minus u. So here we can take x as e raised to minus u, right? So now dx can be written as negative of e raised to minus u du, right? Okay. So now we have obtained the value of dx in terms of u. Now let us change the limits accordingly, right? So here x varies from 0 to 1. So when x is 0, then u is here negative of log of 0, right? And we know that log of 0 is not defined, so this is infinite, right? And when x is equal to 1, we have u is equal to negative of log of 1, and log of 1 is 0, so we have 0, right? So now we can write this this integral I in terms of u. So we have here when x is 0, u is infinite, and when x is 1, u is equal to 0, right? And x cube is replaced by e raised to minus u raised to power 3, and here we have square root of u, right? Because negative of log x is u, and dx is replaced by minus e raised to minus u and du, right? Okay, now let us arrange this integral in a simpler way. So now we can write this integral as negative. We can take this negative sign outside the integral, and we have infinity to 0, e raised to minus 3u. This is e raised to minus 3u. Here we have minus u, so we can write it here. And then we have u raised to half, right? Okay, now what we will do here, we can interchange the limits, and we can neutralize this negative sign, because we know that a raised to a to b f of x dx is equal to negative of b to a f of x dx, right? So when we interchange the limits, then we put a negative sign in front of the integral, and here we can neutralize this negative sign by interchanging the limits, right? So we have 0 to infinity, and here we have e raised to minus 4u, and we can take this u raised to half to the numerator, so this is minus half, right? So viewers, now we have this integral, right? Now let us apply the substitution method to this integral, right? So here we are again applying the substitution method. So let us assume further that z is equal to, here we can take 4u, right? So we'll assume 4u is equal to z, right? So let us differentiate z with respect to u. So dz over du is equal to 4. That is the derivative of u with respect to u is 1. So we have 4. So we can now write dz is equal to 4 times du, right? And du can be written as dz over 4, right? Okay, now see here the limits of integration vary from 0 to infinity. So when u is 0, then obviously z is equal to 4 times 0 is 0, and when u is infinite, then z is also 4 times infinite, that is infinite, right? So now this integral can be expressed in terms of the new variable z, right? So we have 0 to infinity, and here we have e raised to minus z, and u can be replaced by z over 4, right? Because u is z over 4. So now we have here z over 4 raised to minus half, and du can be replaced by dz over 4, right? So now let us simplify this integral, right? So we can now write I as 0 to infinity. Here we have e raised to minus z, and we have z raised to minus half, and we have 4 raised to minus half, and here we have dz over 4, right? Now see, 4 raised to minus half is equal to uh, 4 raised to minus half can be written as 2 square raised to minus half. So 2 and 2 get cancelled. So we have 2 raised to minus 1, and we can take 2 raised to minus 1 to the numerator. So we have e raised to minus z, z raised to minus half. Here we have 2, then we have dz over 4, right? So 2, and we can cancel this 4 by this 2. So we have 2 to the 4, and now we can write this integral as half and 0 to infinity e raised to minus z, and z raised to minus half can be written as half minus 1, and here we have dz, right? So we have taken half outside the integral, and minus half can be written as half minus 1, right? Because here we are now going to apply the definition of gamma function. So viewers, we know that the famous Euler's integral can be written as in the form of gamma function, and we can write gamma of n is equal to 0 to infinity e raised to minus z, and here we have z raised to n minus 1 and dz, right? Where n is greater than 0, right? So the gamma function is defined like this. Gamma of n is the integral 0 to infinity e raised to minus z, z raised to n minus 1 dz, where n is greater than 0. So this is the famous integral, and if we compare this integral with this one, then we can easily see that here we have half, right? And the value of n is equal to half, right? So now this integral is equal to half times, and here we have n is equal to half, so this is gamma of half, right? And we know that the value of gamma of half is square root of pi, right? So here we can replace the value of gamma of half is equal to square root of pi. So we have half times square root of pi, right? So viewers, the value of this integral I is equal to square root of pi divided by 2, right? Hello viewers, in today's class we are going to discuss yet another important and conceptual problem from definite integrals, in which we'll use the method of differentiation under the integral sign, right? So the method of differentiation under the integral sign, this method is also known as the Leibniz Integral Rule, right? So in this lecture we'll see how we can evaluate this integral using this method, right? So here we have the integral 0 to infinity 1 minus e raised to minus pi x square divided by x square dx, right? So let us start. So viewers, while applying the method of differentiation under the integral sign, what we usually do, we take an integral which is similar to the integral which we have to calculate, right? So here I will take an integral 0 to infinity 1 minus e raised to minus ax square divided by x square dx, right? So here we'll assume or will introduce a parameter a in the integral so that we can differentiate this integral I with respect to this parameter a, right? So here this a is our parameter or the variable, and moreover a is greater than 0, right? So while evaluating this integral, we'll take or we'll start with this integral, right? So once we'll complete all the steps regarding this integral, in the final result we can substitute a is equal to pi so that we can obtain the value of this given integral, right? So now see, we will start with this integral, and this integral is a function of a, right? So while applying the method of differentiation under the integral sign, we take the integral as a function of the variable which was introduced, right? So here a is the variable. Now we'll differentiate this integral with respect to this variable a, keeping x as constant, right? So it implies that we have to make use of partial differentiation. So let us differentiate this integral both sides with respect to this parameter a. So we have del I a over del a, and here we have del of del a 0 to infinity 1 minus e raised to minus ax square divided by x square, and here we have dx, right? So now since this is an operator, so we can take this derivative operator inside the integral sign, right? So we can now write 0 to infinity, and here we have del by del a of 1 minus e raised to minus ax square divided by x square, right? Now we have to differentiate this function with respect to a, keeping x as constant, right? So what we will get, we have 0 to infinity. We can take this x square outside this operator, so we have 1 over x square, and now we have del by del a of 1 minus e raised to minus ax square, and here we have dx, right? So now we can write 0 to infinity 1 over x square. Now the derivative of 1 is 0 because 1 is a constant, and the derivative of a constant is 0, right? And here we have to differentiate e raised to minus ax square with respect to a, right? So what we will get here, the derivative of e raised to minus ax square is e raised to minus ax square, and then by chain rule we can differentiate minus ax square with respect to a. So the derivative of a is 1, so we have simply here x square, right? And here we can write dx. So now we can simplify this integral. So we have del IA over del A is equal to, see, we can now write 0 to infinity, and here we have minus minus plus, so we are left with x square e raised to minus ax square divided by x square dx, right? Now this x square and this x square get cancelled, so we are left with 0 to infinity, and e raised to minus ax square dx, right? So now we have this equation. So now see, we have to evaluate this integral, right? And let us take this integral as I1, right? So here what we will do, we'll separately solve this integral. So here we can evaluate this integral by making use of the concept of gamma function, right? So we'll substitute here t is equal to say ax square, right? So we'll solve this integral by method of substitution. So t is equal to ax square. So we can now write x square is equal to t over a, that is x is square root of t over square root of a, right? Now let us differentiate x with respect to t. So we have dx over dt is equal to 1 over square root of a, and the derivative of square root of t is 1 over 2 times square root of t, right? So now dx can be written as dt divided by 2 times square root of a times square root of t, right? Okay, so now here we'll also change the limits. So now see here the limits vary from 0 to infinity, right? So when x is 0, then we can obtain the value of t from this relation. So when x is 0, then t is also 0, right? And similarly when x is infinity, then t is also infinite, right? So now let us write this integral I1 in terms of t. So we have 0 to infinity, the limits remains the same, and here we have e raised to minus t, and because ax square is t and dx is replaced by dt divided by 2 root a, and here we have square root of t, right? So I1 can be written as 1 over 2 times square root of a. Now we can take 2 times square root of a as constant, and we can take it out from the integral sign. So we have 0 to infinity e raised to minus t, and see here we have square root of t. So if we take square root of t to the numerator, we have t raised to minus half, and here we have dt. So now we can write this integral I1 as 1 over 2 root a, and here we have 0 to infinity e raised to minus t, and here we have t raised to minus half, right? And t raised to minus half can be written as half minus 1, right? So that we can convert this integral into the gamma function. So now we know that the gamma function is defined as the gamma of n is 0 to infinity e raised to minus x, x raised to n minus 1 dx for n greater than 0. Right? So this is the famous Euler integral which defines the gamma function. Gamma of n is 0 to infinity e raised to minus x, x raised to n minus 1 dx, right? So now if we compare this integral with this one, we can see that this integral is in the variable t, and here x raised to n minus 1, here we have t raised to half minus 1. So if we compare this integral with this one, then we can easily see that n is half, right? So this integral is nothing but gamma of half, right? So gamma of half is 0 to infinity e raised to minus t, t raised to half minus 1, right? And we know a standard result, that is gamma of half is square root of pi, right? So if we write here the value of gamma of half, so we have 1 over 2 root a, and here we have square root of pi, right? So now the value of this integral, that is I1, is given by square root of pi over a, and here we can write half, right? So this is half times square root of pi over a. So now we can replace this integral by its value half times square root of pi over a. So viewers, now we can write this equation as del I over del A is equal to I1, because this integral was assumed as I1, and I1 is equal to half times square root of pi over square root of A, right? So now we have a differential equation of first order, right? So we can now solve this differential equation for A. So we have del I over del A is equal to root pi over 2, and here square root of A can be taken to the numerator. So we have A raised to minus half, right? So now we can write del IA is equal to root pi over 2 a raised to minus half, and here we have dA, right? And now we can integrate both sides, and here C is the constant of integration. So viewers, whenever we apply the method of differentiation under the integral sign, we first introduce a parameter a, right? And we form a general integral, and then we differentiate that general integral into with respect to the introduced variable, and then we form a differential equation, right? And then we solve that differential equation. So here we have this differential equation. So here di is simply ia. So here we have ia, and here we have root pi over 2 integral a raised to minus half dA plus c. So we have I of a root pi over 2, and the integral of a raised to minus half dA is 2 times square root of a, right? Because here we have used this result, that is x raised to n dx is x raised to n plus 1 divided by n plus 1, provided n is not equal to minus 1, right? So here the value of n is minus half, right? So 2 and 2 get cancelled, so we are left with I of a is equal to square root of pi times a, right? So combining these two terms, we have square root of pi a, and here we have c, right? So now our aim is to get the value of this c, which is the constant of integration, right? And we'll find this c with the help of some initial conditions. So let us find the value of c, right? So what we will do, let us take the conditions as a is equal to 0, and we'll find the value of I, right? So if we take a is equal to 0 in this integral, then see what is the value of I of 0, right? So when we take a is equal to 0 here, then I of 0 is equal to 0 to infinity 1 minus e raised to 0, because a is 0, so 0 times x square is 0, and here we have x square dx, right? And e raised to 0 is 1, right? So we have 0 to infinity 1 minus 1 over x square dx, and 1 minus 1 is 0, so the value of the integral, it vanishes, so this is 0, right? So e raised to 0 is 1. So we see that when we apply the condition that a is equal to 0, then I of 0 is also equal to 0. So now here taking a is equal to 0, we have I of 0 is equal to square root of pi times 0 plus c. So I of 0 is 0, so we have 0 is equal to 0 plus c. So this implies that c is equal to 0, right? So we see that the value of the constant of integration is 0. So taking this c is equal to 0 in this equation, we have I of a is equal to square root of pi a plus 0, that is I of a is equal to square root of pi a. And remember a is greater than 0, right? So here we have obtained the value of this integral, right? So the value of this integral is equal to square root of pi a, right? So the value of this integral depends on the value of a, right? So now we can easily find out the value of this integral, right? So if we replace a by pi, because here we have minus pi x square. So if we take a is equal to pi, then the value of this integral is e raised to minus pi x square over x square dx is equal to square root of pi times pi, because a is pi, so this is square root of pi square, that is equal to pi, right? So the value of this integral is pi. Now, similarly, if we wish to find out the values of these two integrals, then we can easily use this result, right? So, if taking the first integral, we can compare this integral with this one. So, here we have minus 1x square. So, a is 1, right? So, the value of this integral is given by this expression by taking a is equal to 1. So, we have root pi times 1, that is square root of pi. So the value of this integral is square root of pi. And in this case, we have the value of a as 2. So the value of this integral is root pi times 2, because a is 2. So this is square root of 2 pi, right?